So I like this. It's like, well, I don't understand vectors, and at this point, I'm too afraid to ask. Ha ha ha. Listen, if you still are confused about vectors, you need to ask somebody. Ask me, ask a tutor, ask the workshop facilitator. It's time to ask questions because you want to make sure you have your vectors and all the operations with vectors and all the different properties of vectors down cold. Because if you don't, it's going to be a problem, because that's one of the bases of this whole course. It's a fundamental skill and knowledge to be able to work with vectors. All right. So speaking of vectors, I know that physics has a lot of vectors, and I was pretty unhappy when I looked at certain problems off of the quiz, and I took off tons of points, and it's going to be even worse. Okay, I'm going to be really unmerciful when I see people doing problems on your quiz, getting the right answer, but you're using something that looks like you're using a math app, or you're Googling up the answer on Wolfram Alpha, and it has nothing to do with the approach in the book or in my lecture notes or anything. Well, I learned that in physics. Good for you. You got to learn it the Calculus 3 strategy way. And if you're not willing, maybe this isn't the course for you. And it's not, oh, it's Professor Zrasky's way or the highway. No, I am teaching you Calculus 3 skills and knowledge. My experience with people in physics, when they get the right answer for one of these force diagrams, they have no idea what they're doing. Well, mg sine theta, and my physics professor said la 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 la, and I don't even know what I'm doing, but it works. Good for you. I'm not moved. And you do that in any of my quizzes or exams in the future, because we're going to do another thing that's very physics-based when we get to projectile motion. If I see you doing it the physics way, I don't care if your answer is right, 0 points. That's how I roll. Okay, so be open to learning the approaches and strategies and techniques that's supported by your textbook and in my lecture notes. Okay? Yes, I know a lot of times there might be more than one way to skin a cat, but I want you to see the way we do it here. And that's how we're going to roll. Okay? And yeah, I'm pretty hardcore about that. Unyielding. So let's go to, whoops, didn't want to do that. Let's look at cylindrical and quadric surfaces. So I want us to focus on 2 different types. So you're going to learn about cylindrical, which is a terrible name because it sounds like it's just cylinders, but it's not. There are cylindrical surfaces that don't look like a cylinder at all. And then we're going to look at quadric surfaces, which is another kind of animal. So let's talk about the 2 surfaces that you are already supposed to know what they look like and what their corresponding equations are. So one of them, believe it or not, is spheres. That's a surface. You know, it's a surface in the shape of a ball. And we already looked at the standard equation for a sphere. So you know what that is. And you can even cherry pick off the center point if you have an equation for a sphere in standard form. And the radius is the square root of whatever the number is on the right-hand side of the equation, in this case, r. And now the other surface that you've studied is planes. And the standard form for a plane equation looks like this. And what do we put here? What is it? What is this equal to? We have A times a quantity plus B times a quantity.
0.
Plus. Very good. Yeah, I want to see a 0 there. Now, remember when you're finding the plane equation, you need a point on the plane and you need a vector n that's normal to the plane. So this vector, oh, they're doing v. So the vector v, what are the components of that vector? Can you cherry pick them off the plane equation? Go.
ABC.
Very good. And then the order triple for the point on the plane is given by, you can cherry pick that also, right?
X, Y, and Z.
X, Y, Z.
X0, Y0, or we call it X naught, Y naught, Z naught, or X subscript 0, Y subscript 0, Z subscript 0. Okay, so those numbers, whatever those numbers are, you know, like 2, 5, -2, whatever, those numbers are going to be the coordinates of a point that lives on your plane. Okay, so that was just a quick recap of the surfaces that you're already supposed to know. And please don't lose sight of either of those, because I'm going to try to trick you in future quizzes. I'm going to teach you about these new surface equations, and then I'm going to secretly throw in the old ones to see if you're like, oh, I forget the old ones. I only know the new ones now. No, you got to know everything. Everything's in the mix now. Okay, let's do cylindrical surfaces. This is a 3rd type of surface we're studying in this class. Unfortunately, they call it a cylinder, and it's a misnomer because most cylindrical surfaces look nothing like cylinders. But a cylinder is the easiest one to start with. So here's how they do it. When you see one of these cylindrical surface equations, it will look something like that, where one of the variables is missing. Well, which one? It doesn't matter. One of the variables will be missing. So there will be two variables for sure, but one of the variables is missing. That's sort of a trick way, and that's the way, full disclosure, how I figure out I'm dealing with a cylindrical surface, if I see one of the variables missing. Now, folks, everybody in this room should have an idea of what that equation is from an algebra class. In your algebra class, I hope you get that this is a circle of radius A centered at the origin, right? But in this class, Calculus 3, it is not just a circle centered at the origin of radius A, but that actually is going to start us off. So you're actually going to graph here in the XY coordinate plane the circle centered at the origin of radius A. And then in 3D, you're going to draw that circle there in the XY plane. And then that's called the generating curve. And then you're going to whoosh it. Whoosh is not a technical term, but I made this up. You're going to whoosh it in the direction up and down of the missing variable, parallel to the missing variable's axis. In this case, the missing variable is Z. And so when you whoosh this circle in the direction of the missing variable, you get the surface. So that is how you get one of these cylindrical surfaces, okay? So here's the official definition of a cylinder. You've got a curve in a plane, doesn't have to be the XY plane, and L is a line not in the parallel plane. And these lines that I put here, those are the lines they're talking about. Those are called rulings, those lines that are parallel to your missing axes. And sometimes they call this generating curve a directrix. I never do, but that's just some more vocabulary for you. Why do I have this problem here? I would call it whooshing forever, Nicholas. I had a student in my class about 3 years ago, and let's just say he really liked a lot of attention. He would raise his hand like every 10 minutes just to say something. And I remember when I did the whooshing, he goes, I think you should use the word extrude. So, oh, okay, I'm going to just say that you extrude the generating curve in the direction of the missing variable. And that is probably a more exact word, more precise, but I still like the whoosh. Okay, now let's look at equations of cylinders definition here. The equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the other two axes. That's what I mean about a missing variable. So AKA, you've got a missing variable. Okay, so let me walk you through these other ones that are done here. Let's say you didn't know that this was the answer. You're like, I don't know. And they gave you y equals x squared. And they said, go graph this. And you're like, well, I don't know. In my algebra class, that's a parabola. And I would say, good start, actually. Good for you. That's your algebra class is the perfect step one. So step one is you graph the generating curve, I'll abbreviate gen curve, in this case, the XY plane, because those are the variables we do have. And this is easy because it's just a parabola. Okay, so there's y equals x squared. Now what? Now try to draw that generating curve again, but be in 3D. So in 3D, and this is the part where a lot of students kind of choke, is how do you draw this correctly in 3D? So if you'll notice, it's going in the positive y direction. So this upward parabola looks like that when I draw it here in the XY plane. And then I'm going to whoosh it in the direction of, I hate my Microsoft Surface Pro. I'm going to whoosh it in the direction of the missing variable. So that's up and down. And when I whoosh it, and this is hard to draw in 3D.
The PDF annotate. Oh, there it is.
When I whoosh this in the direction of the missing variable, I get that. So you can see it almost looks like a piece of paper that's vertical and that's curled. Does everybody see this? So there, I just whooshed it.
Yeah.
And then
Yes.
this right here is the answer. This is a weird surface. It's you know, sort of a sideways extruded parabola. Let's do another one. What about y equals z squared? The missing variable now is x. Okay, fine. So in the yz plane, you have to graph y equals z squared. And be careful, because that is not a vertical parabola. I claim that this is a horizontal parabola. Well, how do you know? Well, because here, z, you can think of z as being the dependent variable. So this is going to be a horizontal parabola. So how do you draw that in 3D? And again, this is the answer right here, but how would you get that in slow motion? So I'm just trying to get you the answer, all the steps, the intermediate steps on how you would get it. Because you wouldn't just go, yeah, there it is. Now, certainly, there are graphing calculators on the web where you can go and just punch it up, and then there you have it. But if you're doing this by hand and it's, nobody has any apps or software. So here in the YZ plane, so folks, this is the YZ plane right here. You're drawing this sideways parabola here in 3D now, and so you're going to draw it like that. But you're not done, because that's a curve now. You got to whoosh the curve to make the surface. You're going to whoosh it back and forth in the direction of the x-axis. You're going to like take it and whoosh. And so when I whoosh this, oh boy, this is not easy to do. I get this sort of sideways surface. And of course, here's the actual answer. And that's the parabola y equals z squared for you in the in 3D. Okay, so now let's look at a couple other ones here on the next page, just so you can get a hand at this. How would you do, say, z equals sine of x? Well, in this equation, the y variable is missing, just the one variable. So that's how I know it's going to be a cylindrical surface. It ain't going to look like a cylinder, though. But here in the xz plane, you can draw, sine of x, which is going to look like a wave like that. Well, how would you draw that in 3D? And I'm just going to pick a portion of this curve. How about if I just go from 0 to 2 pi? Otherwise, it's going to be a little bit crazy. So here's x, here's y, here's z. The xz plane is this right here. So when I'm drawing that little piece or portion of the sine curve where I'm in the xz plane and I'm going from 0 to 2 pi in the positive x-axis direction, there's a little piece of my sine curve. And now I need to whoosh it in the direction of the y-axis. Oh boy, this is always kind of fun. So this is a little bit tough, but hopefully you can picture this. And it's sort of like a curvy curved surface there. Not bad. And I'll do one more. So this one is a cylindrical surface because it's an equation with x missing. Okay, fine. So in the YZ plane, so this is the YZ plane, I'm going to draw the generating curve. But that's just a circle centered at the origin of radius 2. So there's the generating curve, fine. Then draw the generating curve in 3D and get ready to whoosh it in the direction of the missing variable. So here in 3D, you're going to try to draw this circle in the YZ coordinate plane with a radius of 2, like that. And then you're going to whoosh it back and forth in the direction of the x variable parallel to the x-axis. And this actually is a cylinder. It's like a sideways can or a sideways cylinder. So there's another cylindrical surface, and I'm done covering cylindrical surfaces. I'm going to stop there and take a pause and questions.
For step 1, when you draw stuff in the two-dimensional plane, how do you pick the variable for the vertical axis and the variable for the horizontal axis?
Well, you stick to this convention that if you've got z involved, z is always the vertical axis. And if you're just doing the xy plane, then just by tradition, your y will be the vertical axis. Does that help?
Yes.
So here's how the xy plane would look. Here would be the xz plane, and then here would be the yz plane. Those are your 3 choices, and that's it. Does that help?
Yes, helpful.
Okay.
Thank you.
Yeah,
Now, I know that the physics folks, for those of you who are like, well, in physics, our z-axis isn't vertical, whereas ours is like coming out of the paper. And I'm like, that's nice. We're not going to do it the physics way. We're gonna have a different convention. I remember one of my students, this is from like more than 15 years ago when I was teaching this class, and she was an A student. She was so good. And she ended up going to UCSD and got her engineering degree. I actually ended up getting invited to her wedding, which was actually fun. But long story short, when she went to take the next course after here, this Calculus 3, I think it's Math 20D, D is in dog over at UCSD. That's sort of this course on steroids. It's got a lot of elements of this course in it, but they really kill you with all sort of extra stuff. You've got not only vectors and some of the vector calculus stuff we do in there, but other stuff. So they had some really weird conventions in that class when it came to notation and order of spherical coordinates. And I was like, but Lisa, don't worry about it. You're going to be fine. It's just a different convention. You know this stuff. And she ended up doing okay. Okay. She just needed a little hand holding. Shoulder to cry on for half an hour, and then she was good. Okay, now let's switch our attention. New topic. Okay, so now you know what a cylindrical surface is. There's infinity cylindrical surfaces, and most of them never look like a cylinder. They could be kind of wavy or curvy or who knows. Let's talk about quadric surfaces. This is another kind of surface that's very specific. But by the way, when we get done with this section, cylindrical and spherical, don't think you know everything about surfaces. There's infinity different kinds of surfaces out there. We're just looking at some special cases out of all the infinity possibilities. Okay? So what the heck is a quadric? And by the way, Briggs does a very poor job of doing this. So I'm going to do it a different calculus book approach. I think it's better. So what's the quadric surface? Now, let me start with something that you know, and then get so that you can get better what you don't know. So in your pre-calc days, I'm hoping that you studied conics. Does anybody remember studying conics or conic sections? Let's take an informal survey. I'll check the chat. Do you guys remember conics, or?
It definitely happened.
It happened.
It was a thing. Yeah.
It's a thing. Yeah, it was there. We did something, but don't give me a quiz on it. I have no idea. Once I remind you, I think you'll be fine. So the idea is if you've got a double napped cone, conics comes from cone, and you take your knife and cut it in different ways, you'll get some different curves when you look at the cross section of your cut. So if you took a knife and you just cut straight across here and you examine the cross section, do you get that you'd get a circle? That's a conic section, a circle. Well, what if you took your knife this time and you cut a little bit at an angle instead of horizontally through your cone, and then you examine the cross section. So instead of a circle, you would get an ellipse. That's one of the conics. Another thing that happened with your knife here, if you cut through the top and then you come out of the side and you examine the cross section there, you get a parabola. That's one of the conic sections. And finally, and this is where you have to this is why we have a double nap cone. If you take your knife and you start at the top and you cut through the cone, not through the center because that's uninteresting. You cut sort of at an angle, not an angle, but off to the side and then straight down. Let me do pink. So your knife comes through like this, chop, then you get a hyperbola. You get an up and down going on here. That's another conic section. So these are the four curves that you study when you study conic sections. Does anybody remember these and the equations that go with each of these?
Yeah.
I remember the ellipse was like the equation of a circle. However, it was divided by 2.
Well, divided by where you have different denominators for the x and y terms.
Thank you.
Yeah, so like an ellipse equation has this look to it in standard form. And you're going to have to know this stuff for later, so it's worth revisiting. That's an ellipse equation. If these denominators were equal to each other, you would have a circle. Okay, now let's talk about quadric surfaces. So how is this similar to conics? Because in conics, you're looking at equations that have ax squared plus by squared plus cxy, say, plus ax, or excuse me, I'm going to use a different, dx plus ey equals f. You're looking at equations that have that format, where x and y can be squared, and they have coefficients, and then you might have a rotating term, although usually they try to avoid that one. And then you have some first order terms, and then your constant, okay? But now we're gonna look at equations that have this big old form. Oh my God, because we're gonna throw a z into the mix. So again, we're gonna have x squared and y squared terms, but we'll also have a z squared term. We'll also have an x term and a y term like we did before, but a z term. And we still have a constant term. And then we have these three type of terms that are rotating terms that can like turn your surface sort of sideways, off kilter with respect to the coordinate axes. I'm not going to have us worry about that too much, but there's 6 basic types of quadric surfaces. And again, please don't memorize this stuff. You know, you'll have access to your notes and so on when you take a quiz, so you'll know. So hopefully you learned from taking the quiz the other day that a trace is when it's a curve that you get when your surface cuts through one of the coordinate planes. Well, how do you find a trace? You set the proper variable that isn't in that coordinate plane, the missing one, to 0, and then you can get a trace. So to visualize any of these quadrics, it's really helpful to look at its traces in each of the planes. Okay, so, and this is the key why I went over conics. The traces of quadrics are conics. So the traces will either be an ellipse, a circle, a parabola, or a hyperbola. And there are some traces that are sort of the ones that are deteriorated, like lines and points. That can happen. Okay, now let's do our quadrics. So I'm not going to cover each and every one of these in massive detail. I just provided these pictures for you for all 6 types. So you're going to be responsible for, if you're given an equation, kind of having an idea what it is. And the ones that I always kind of know right off the top of my head, ellipsoids are kind of easy to remember because they look like an ellipse equation, but you have an extra term with a z squared in it. And they're showing you a picture of an ellipsoid. I think of it as kind of looking like an egg, a little bit, sort of. A hyperboloid of one sheet, the formula for it looks almost like an ellipsoid, except for one of the squared terms is a negative. It doesn't necessarily have to be the z squared term that has a negative. If it is, then your hyperboloid is basically parallel to your z-axis. If one of the other x squared terms were negative, then it would be flipped over on its side parallel to that axis. Here's a hyperboloid of 2 sheets. So you have 2 negatives in there with a 1 on the right hand side. They're just giving you all the different traces. The 3 other quadrics are elliptic cone. These are important. You should be able to memorize these. Typically, you'll see cones, a basic cone will have this equation where you move this z squared term to the other side. And notice instead of a 1 here, we have a 0. That's a big difference from the previous page. So one of the things that all the surfaces on this page have in common is they all have a 1 on the right-hand side of the equals. On the second page of pictures, you'll notice that this is a 0, and you could get everything on one side and have a 0 for the other 2 types, although they solved it for one of the variables. It doesn't have to be z. But elliptic paraboloid is very common surface we're going to use in this semester. And a hyperbolic paraboloid is kind of cool. I like to think of it as a horse's saddle because it kind of has that look. If you're into horses. I have a couple friends that are. Okay, so those are all the formulas, blah, blah, blah. Okay, fine. So let's say you had a quiz question like, oh, okay, classify and sketch this surface. Well, you could just go get a graphing, go into GeoGebra, type it up, boom, there it is. But let's say you didn't have a graphing calculator. How would you do it by hand? First up, I would get this constant term on one side and keep everything else on the other. So that means I have a negative 12 there. Now, all those equations you saw there technically either have a 0 or a 1 for its constant term. So this one, I need to get a 1 here. So how do I make this a 1? Divide both sides by negative 12. So I get a 1. And then I'm going to split this up into separate fractions. and reduce to lowest terms. And then I look at all the possibilities, which, and this is a negative here, which one of the possibilities on page 1, because that's the page that had the 1 on the right-hand side, has 2 of the terms negative. So the only one that has 2 of the terms with a negative in front of it is a hyperboloid of 2 sheets. So that's what this thing is. It's a hyperboloid of 2 sheets. With the y-axis as its axis. Now, if you want to get into, let me pull up my 3D software here, my favorite 3D software. Where is it? Right here. So this is what I love about this graphing app, is it allows me to graph stuff without even telling it what I'm graphing. It just takes any equation. And GeoGebra does that too for the 3D graph, right? It just knows that you're doing something in 3D. So if I just type it in as is, the way it was given to me, like, okay, plus 12 equals 0, hit it, it's not satisfied in the coordinate ranges given. Oh, hang on, let's see here. Parameters. Oh, maybe these parameters are off. Let's see if I change these. I'm hoping this works. I don't know. Maybe it's not happy today. Go over here. I don't know. Otherwise, we'll go to GeoGebra. There's always that to save us. Now I'm just trying to change my X and Y Z parameters. Let's see if that helps any. So these should all be okay. Let's see if I try it now. Ah, there we go. So there's my hyperboloid of 2 sheets. So it's facing forwards and backwards to the positive and negative y-axes right there. And because it's an implicit equation, I don't have all the choices for colors like I did for explicit functions, which we'll look at. But I could change it to blue. Ooh, that's pretty. Purple, nice. Frost, okay, fine, whatever. Okay, so that's a hyperboloid of 2 sheets. There you go. Okay, so they talk about getting the traces here. They've kind of done the problem for you. If you want to see what the XY trace is, set z equal to 0 and examine that resulting equation. And so when it cuts through the XY plane, it looks like a hyperbola if you just look at that cross section. So is that really true? Like if you look at this, can you imagine that if you just examine what was going on in the XY plane, whoo, too much twisting there, you would have a hyperbola. So yeah, it looks like that would be the case. Okay. So on the next page, I have a picture of it so you don't have to draw it. So there we go. There's infinitely many kind of surfaces out there that don't fit any of the 4 categories that we've discussed so far. What are the 4 categories? Planes, spheres, cylindrical surfaces, and now quadric surfaces. That's all very limited cases. There's so much more there. But it's a good start. So we're officially done with chapter 13. Congratulations, class. You are now blessed. You're graduates of chapter 13. Okay? You learned everything there is to know in there. We did vectors, everything we wanted to know about vectors, dot product, projections, cross product, you know, and all the theorems that go with it. And then we looked at lines and planes in space and coming up with equations for that. You had to know about vectors to even discuss lines and planes in space. And that's why we had to study it first. Okay? So before we move on to chapter 14, while I get all this queued up, does anybody have any questions? We'll stop here. Pause.
Isaiah has a good question in the chat.
Okay, let's see the chat. Yeah, all right, shoot, I got it. That doesn't really look like a question to me, but okay. So onward and upward. We're doing chapter 14 now. Drones. Drones? Yeah, sure. Drones. Okay. So right now, what I'd like to do is do a sort of a little preliminary, what do you know, and then we'll do what you don't know. So you can kind of start sort of relating things. That's my point. So now that we are starting chapter 14, we're going to be starting, we're going to start by introducing you to a brand new function, and then we're going to start doing calculus on those brand new functions. That's how we're going to roll. So we're finally going to start calculus, and we're going to start it today. So what is calculus? It's limits, derivatives, and integrals. And you have to have those skills very strong in this course. You have to know how to take limits. You have to know how to take derivatives. You have to know how to take integrals. And also to find domains of functions, which you learned in hopefully a pre-calc or algebra class. So that we're going to do that too. So the math is getting harder. Oh yeah, this class is going to start hitting it. Okay, and some of you are like, well, I thought this was going to be easier than Calc 2. Well, it is in some ways and it isn't in other ways. Okay, the good news is we don't have sequences and series. Okay, fine. But you still have a lot of other new stuff. So I'm going to insert a page above. Let's see here. So the reason why is I want to give you sort of an overview of what we've done and where we're headed. I didn't do this on day one because I didn't think you were ready. So here's Calc 3 in a nutshell. Okay, I'm going to draw you 4 boxes, 5 boxes, but they're sort of 4. So what am I saying? So good news, you already finished one of the boxes. So congratulations, you did vectors and fun and play with vectors. And in there, in the mix, we talked about planes and lines, but we did mostly vectors. Okay, so you're done. Now what? You move on. The next big chunk of knowledge that we need to go over is contained in this next chapter, chapter 14. So this was chapter 13. We're now going to do chapter 14. And we're going to learn about vector valued functions, which is a fancy schmancy name for curves in space. That's all it is. So in this block, you're going to look at this new kind of function. You're going to look at sketching it, domains, limits, derivatives, and integrals. Okay, fine. So what? Then the next big block, and I'm going to make sort of a big block like this. It's sort of I'll put a dotted line through it. This is the multivariable calculus part of the course. That's going to be later, but you're going to do chapter 15, and then you'll do chapter 16. And together as a pair, those comprise the multivariable calculus portion of this course. So you're going to look at functions of more than one variable. What else do we do there? Well, that's why you're taking the class. But briefly, you're going to look at something called partial derivatives and all the applications of partial derivatives. I'm being very simplistic now. And things like that, like gradients and stuff like that. And then in chapter 16, you're going to do more multivariable calculus. This is the integration part, but it's called multiple integration. This is the part where you're going to be doing double and triple integrals and some of the uses of double and triple integrals. And then finally, the grand finale of this course is going to be the vector calculus portion of this course, where you need all of the previous knowledge just to be able to understand it. And we're going to be doing some very powerful stuff in there, a lot of physics stuff like divergence and curl. We're going to be looking at vector fields because we're going to be studying vector fields in mass detail. And we're going to be looking at flux integrals, surface integrals. We're going to be doing Green's theorem. So you'll be able to calculate circulation and flux in 2D. Then you're going to look at the divergence theorem and Stokes theorem and all sorts of fun stuff. But you need everything that came before it in order to even understand it. And this includes some of even the basic building block tools that we talked about in the last 2 weeks, like unitizing a vector, projections, all that stuff is going to come into play. And if you're not strong and you don't have a good skill set with that, then the rest of this course could be an unholy nightmare for you. That's all I'm saying, okay? So with that in mind, let's now hit vector valued functions. So let's do a little bit of review. You actually did number 1 in Calc 2. I did? I don't remember. Was I there? Yeah, you were there because you're graduates of Calc 2. You did describing a plane curve with two parametric equations where x was some function of t and y was some other function of t. You did that. And we're going to do some more today, so I hope you brought your graphing calculator because we'll do some graphs of it. So now we're going to jack it up. We're going to take your Calc 2 knowledge and jack it up one level. What do you mean? We're going to add a z-axis in the mix. And so we're going to have work with three parametric equations where x is still a function of t, f of t, y is a function of t, but now z is also a function of t. Cool, and those are the parametric equations for a curve in space. So you can't use your graphing calculator to graph it, but you certainly can use some graphing tools online. Okay, so before I introduce the vector valued function, because I don't want to do that yet, I want to do a quick review. Let's talk about a function that you already know and love. So the review is, let's do a function that you're supposed to be very familiar with, a function of a single variable. And if you don't know all the wherefores of a function of a single variable, we're in trouble, because you're supposed to have covered that in pre-calc, Calc 1, and Calc 2. What do you mean? Well, look at, y equals f of x. That's a function of a single variable. You know everything there is to know about one of those guys. You can find its domain, do the limits of it, derivatives, integrate. So I like to do the function machine because we're about to do domain and range for a vector valued function. If you're dealing with a function of a single variable, like you studied in pre-calc and Calc 1 and 2, what are the elements of the domain and what are the elements of the range? So I'm going to give you some choices. When you plug something in, if you will, into your function y equals f of x, are you plugging in a point, a real number, or a vector? So here's the domain. I'm feeding something into my function machine, and he's going to eat it. Does he eat a point, a real number, or a vector? I'm going to open it up. I'll check the chat.
We're all looking at like a 66.6% chance of being right? Like,
Well, I don't know. Your choices are, do you feed it a point? Do you feed the function a real number? Or do you give it a vector to eat?
Is it a real number?
Thank you.
Oh.
So you feed it a real number, x. So he goes, thank you very much. I got my x. Yum, 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 yum. So he eats a real number, not a point, not a vector. Well, what about points? Well, points are what you get after you feed the function the number, and then you combine it with his poo-poo. What is his poo-poo? His poo-poo's down here. He's going to poop out something. So your function here, y equals f of x, does he poop out, this is the range, here are your three choices again, does he poop out a point, a real number, or a vector?
point.
Real number.
Good thing we're going over this because...
Oh, no.
Another real number.
Real number.
Another real number, thank you.
Oh.
He poops out a y value, okay? So the point that I'm trying to make, well, maybe the point is we need to retake pre-calc, I don't know. You feed the function a real number, like 2, and, let's say the function is y equals x squared, 2 squared, and then he poops out a 4. Now, what do points have to do with it? Well, a point is something that you gather, you get the x and the y together, you get those together in order to help you graph the function, okay? But those aren't what you feed the function. Like, he doesn't eat an ordered pair. Well, yeah, he does. No, he doesn't. You feed him a variable some number x, and then he poops out a y value. That's it. And the ordered pair just helps you graph the collection of points. Now let's go to a function that's new. Okay, we just covered a function that you reviewed it. So there's another function called vector value function. So here's the input spout, and here's the output spout, the poo-poo spout. So when you have a function that's a vector valued function, because it's got the word vector in it, you're going to use angular brackets. So the 2D version would be where you have a function of t as the first component, and a function of some other function of t is your second component. So that's the 2D version. The 3D version looks almost the same because you're going to be able to deal with both. So the 3D version, and by the way, I want to see vector notation. So you're going to put little arrows across the top, would be angular brackets. You'd have a function of t, comma, a function of t, comma, a function of t. So basically, I hope that if you're a thinking student, and this is what you could be thinking, and if not, I'll put the thought in your head. For the 2D version, you simply take these parametric equations and you jam them into a vector. And that makes it a vector valued function. And the graph is still going to be a curve. For the 3D version, you just take these 3 parametric equations and those functions of t, and those become the components in your 3D vector valued function. That's it. So you take your parametric equations and stick them into a vector, and it becomes a vector valued function. So that's why I like to say that a vector valued function is like the love child of parametric equations and vectors. If they were to have a baby, you would get a vector valued function. Okay? Now, let's talk about the feeding, the feeding and care of your baby here. Oh boy, I don't know what just happened. So if you are going to feed something to your vector valued function, whether it's a 2D vector or a 3D vector, it turns out that the domain is also a single real number. You feed it a value of t, and t typically is time. You feed it like, here's time equals, 1 second or 2 seconds or -1 second. You can do negative time. Now the poo-poo, the range, he's going to poop out a vector. And if it's a 2D vector valued function, he'll poop out some 2D constant vector with some actual numbers here. And if it's a 3D vector valued function, then he'll poop out some constant 3D vector. Okay? And there you go. There is a vector valued function block diagram for you. Okay? And then down here is the official definitions. And in this official definition, I want you to notice, instead of using component form, they use the IJ or the IJK. But component form is just as good. So, you get to pick either one. But in your homeworks, you'll probably get them in either possibility. So be ready. So this is the linear combo of standard unit vectors. So either way, so everything we went over in the first 2 weeks of class with vectors, where you could either describe your vector in component form or your vector as a linear combo of the standard unit vectors, is true for vector valued functions. Okay. Let's talk about graphing. When you graph a 2-dimensional vector valued function, you basically just whip out your graphing calculator and you graph the parametric equations, and that gives you the graph. But let me tell you what the real deal is now that you are here in the world of vector valued functions. What happens is you actually get a collection of 2D vectors, not a curve. So I'm just going to make up a whole bunch. And then the actual curve that you see on your graphing calculator when you actually use it in parametric mode, the tips of all of these vectors, this collection of vectors, if you connect them all together, and then you do have an orientation, so you're going to do it increasing values of time, and then the actual vectors themselves get erased. So you're basically connecting the tips of all the vectors. And that's what you see, what a graph of vector valued functions are. So you get a curve. So here it is in 2D, but they erase these vectors, so that's not really what you see. You see the curve. And in 3D, you would get a collection of these 3D vectors, but they erase them and just connect the tips. That's it. So now I want to do some plane curves. This is like a review of Calc 2, so you're welcome that I'm even doing this for you because I don't have to. But I have a feeling, a funny feeling, that a lot of us in the room, because it was maybe the last day or week of the class when you took Calc 2, you completely forgot how to do graphing vector valued functions. So I encourage you, if you have a graphing calculator, to go grab it right now.
I had a quick question, Professor.
Sure.
I just wanted to verify position vectors in this case, they're always coming from the origin?
Yes. Because if you're
just making sure that they get...
But of course, Salo, because you're in component form or you're getting IJK form. So by definition, it's understood that the initial point is in fact the origin. Yes? Okay. Don't look at this. This is some other crap I was doing for my Calc 2 students the other day. But here's the deal. If you go into mode and you go down here to, right now it's in func mode, but if you use your arrow keys and try to get yourself into PAR mode, that stands for parametric, hit enter to actually choose it and then quit out of here. When you click on the Y equals menu, you'll notice it wants X1t and Y1t in terms of t. T is the typical parameter for these parametric equations. And so I'm going to clear out some of this other crap that I had when I don't know what the hell I was doing the last time I did this. And then I'm going to graph the first lecture notes here, t squared, t cubed. So you're going to go t squared for my first parametric equation, and then t cubed for my next guy. Now, before you hit graph, don't hit it yet. You want to check your window because I like to make sure I get the whole picture. If I don't have my T-min and T-max queued up appropriately, I may only get half of the graph drawn out for me. And right now I actually would have. Like, let me just do this. Let's leave the T-min 0 seconds and the T-max 6 and some change. If I hit graph right now, and by the way, don't blink, because these curves have an orientation, and if I don't see the orientation curve, it's wrong. So you'll notice it was half a parabola, and it whooshed upward. But this is only half the graph. So what do you mean? Well, if you let your T minimum be -10, you can have negative time, and then hit graph, you'll get the whole picture. So it actually looks like a sideways flying seagull. What? Yeah. So this actual curve, if I were to graph it down here, looks kind of like this, and orientation matters. You're going to go like this and like that. And you only need one arrow to indicate the direction of it. That's called orientation. And yes, it matters, orientation. And it's going to matter all the way till the very last day of class. Orientation, especially when we do greens. And we're done with letter A. Okay, let's do letter B. I'm just whipping out my calculator and drawing some fun stuff. So letter B, we're going to have two parametric equations. We're going to have cosine t, sine t. So go back to y equals, and you can clear these using your clear button. And let's see, I'm going to have cosine. Oh, let me check mode first, because you got to be in radians mode to graph trig stuff. Oh, okay, I'm in radians mode. Great. Okay, I'm good. So if I go cos t, and I'm not even going to do a closed parentheses because I'm lazy. And then sine t, and then my window I already have probably -10 to 10, which is actually overkill for this particular curve because it's going to actually wrap around itself more than once. I claim that if I only need 0 to 2 pi, and I think 6.28 is 2 pi. T-min is 0 and T-max is 2 pi. That's plenty to get the full picture. So when I hit graph, and I know that looks more like an ellipse rather than a circle, but believe it or not, that's a unit circle. And if you don't believe me, you can click on Z standard, Z square, number 5, and then you can see it really does, and it looks kind of like a crappy circle. But anyway, so there you have it. So what if you do part C, where you have your X equation be sine and your Y be cos? What do you think is going to be the difference? Or is there a difference?
I think orientation is different.
Orientation, correct, is the only difference. So it's still going to be a unit circle centered at the origin, but it's going to be oriented how? Clockwise or counterclockwise?
Clockwise.
Yeah. So if you go to your lecture notes, let's make sure we write all this stuff down now. So the letter B was a little unit circle here. Oh man, I can't draw. And that was counterclockwise, so I'll draw the arrow that way. This guy was a unit circle, but it was clockwise. Okay? So same graph, but the orientation's different. Okay, now the next set of equations, we're going to make it harder. We're not only going to graph it, we're going to try to do something called eliminate the parameter. What the hell? When you're eliminating the parameter and you're giving a corresponding rectangular equation, you're basically trying to kill off the t, the variable t, and instead of two separate equations like the vector value function has, you want a single rectangular equation, a single equation that doesn't have the variable t in it, but it has x's and y's only. That's all. And we did this in Calc 2. For those of you who had me for Calc 2, I made you do this. In fact, you probably had this very same lecture. Go check your course reader. I give Calc 3 lecture to my Calc 2 students. Yeah? So first, let's just look at the graph. Like if you go, okay, well, what does that graph look like? I don't know. Where's my calculator at again? I don't know. T squared minus 1 is the x component. So I'm going to go t squared minus 1. And then the y equation is just t. Oh, nice. And I'm going to check my window. I want to make sure I have a negative. And I'm going to, just for kicks and giggles, I'm going to make my t max be positive 10. So my range is negative 10 to positive 10. And then when I hit graph, whoa, I get a sideways parabola. Yikes. Did anybody notice the orientation here?
Up to, or sorry, down to up.
Yeah, it's like this. Okay. Now, how do you kill off the parameter? So this one is a super easy problem, and I usually never give something this easy. But just to boost your self-esteem here. You want to pick, first you write down the two equations. Your x component is t squared minus 1, and your y component is t. So then you go, you look at your two equations, and you pick the one that's easier to solve for t. Well, t is already solved for because t equals y. So you don't even have to do any algebra. You're like, what? T is equal to y. And you're like, okay, fine, then just substitute. And so the single rectangular equation that matches this graph is x equals y squared minus 1. Do you believe it?
Yes.
Isn't this a horizontal parabola? Yes, and x equals y squared minus 1 is a horizontal parabola, so it works. And this is what this is the answer right here. It's a single rectangular equation that matches the graph that no longer has the parameter t in it. Let's do another one that's harder now. So what about this vector valued function? What does his graph look like? I don't know. You can guess, but I'm not that good. So the x component is square root of t. That's good enough for me. And then the y component is 3 minus t. Fine. Now, because we're doing a square root of t, even though my window has t going negative, the calculator will ignore it, although it should give you an error, like, well, we can't take square roots of negative numbers. You know, what are you doing? You're making me doing something yucky. You're getting in the world of imaginary. And we're not graphing imaginary. It's like, we're not in the complex plane. By the way, you can graph imaginary stuff, and if you took differential equations already, I know some of you in the room did, you should have worked with the imaginary plane, the complex plane a little bit in your course. Because when I teach that class, I go bonkers about teaching complex numbers and working in the complex plane. Why? Because us electrical engineers need it. So if you didn't do that, you'll get a refund. Okay, so I'm not going to change this, but truly I should change the t minimum to a 0, but let's just hit graph anyway. So I claim that this answer here is a half of a parabola, and it's oriented downward. So if you're going to draw this on your paper, it turns out that this vertex of this sideways parabola is right there at the 3, and it goes down. Now, how do you eliminate the parameter? Well, you write down x equals square root of t and y equals 3 minus t. And then you pick which one of these looks like it's easiest to solve for t. Now, they're both about the same as far as solving for t, so it kind of doesn't matter. 6 of these, half a dozen of the other. So I'll just pick the first one. So what do I need to do to both sides of this equation, the x equals square root of t, to solve for t? What should I do first?
Square both sides.
Square both sides, sure. And then I get t is equal to x squared. Beautiful, I just solved it for t. Now you're just going to substitute into the other equation, and you're almost done, except you're not done, because I'll mark you wrong. Well, that's right. Well, the reason why that's not all the way right is we need an extra statement here, comma, something. What's the something? We need to restrict the domain. Because folks, if to be honest with you, the reason why I know this is not true is if you graph 3 minus y equals 3 minus x squared, don't you get the entire parabola? Say yes.
Yeah.
Use right.
Can you guys hear me? Because my internet might go out.
Yeah, we
Yes.
hear you.
Can you guys hear me?
Yes.
Keep talking because I might bomb out of Zoom and have to get back in. My internet looks like it's going wonky today. It's one of those days. Yesterday was bad. Today could be worse. Wonky internet is my middle name. And we spend $100 a month extra here in my house. I've got all this extra stuff for my Wi-Fi. It still sucks. Okay, so this is not good. So what we have to do is we're going to have to cut half the parabola off to make these graphs match. And so what I claim is you're going to have to put an extra statement there where you restrict your domain. As long as x is greater than or equal to 0, then we'll have the right-hand side or the right half of my parabola, and then it will match the vector valued function graph. And I'm done. So keep that in mind. Okay, let's just do a couple more here. And my internet's going south. It sucks. Okay. All right, so how about this? If you graph this using your graphing calculator, what does this guy look like? It's not a circle. What is it?
An ellipse.
Are you guys still there? Yeah, you're right. It is going to be an ellipse. So, oh my goodness. Well, how do you know? Well, you know, graph it and see. And if you go 4 sine t, okay, and then graph it, and then which is the orientation? Ooh, there it is. It looks like it was oriented counterclockwise when I was doing that, I think. Okay, and it is. So it turns out that the y-intercepts are 4 and -4, and the x-intercepts are 3 and -3. And then we had a counterclockwise ellipse. Now, how would you eliminate the parameter? This time you don't solve for t. Why not? Well, then you're going to get like arc sine or arc cos, and it's going to be a nightmare, and I don't even want to see that. Like, oh, well, it's the right answer, and I'm going to go, no, minus 10 points. So how you're going to...
Oh,
Oh, is she
No.
gone?
Bye,
Yeah.
Professor.
All right. Someone here has to pick up the torch, like whoever the meeting assigns the host. Jordan Miles, it is time. All right. All right. I guess it's not time.
I don't know how to do this. Okay. Should I pause the recording? Because it's still recording.
no.
You can pause the recording, no way.
Yeah, I have complete control over this, and I don't want to do this. Like, I can put us in breakout rooms. I can do polls. I can, like, kick people out of the room. I don't like this power. I don't have the necessary credentials for this yet.
This power grants you the ability to solve for x and y in a fashion that's, like, limited to the given domain.
Nah, it doesn't do that.
Right.
Should I pause it? I don't know what to do.
Just let it roll.
Yeah, just let it roll.
Yeah, I don't know, man. This stuff is still sketchy for me, man.
This is going to be an internet archive video.
This is great.
Kids 50 years from now are going to listen to this. This is
I hope
what your
so.
grandfathers had to go through
back in the way back times of
back in the day.
of COVID-19.
Back in the day when, like, what's it called? Like, internet was still a thing, and like people 50 years from now will have, like, I don't know, like just
Neuralinks.
direct plasma.
internet's gonna be
like,
installed in their
neural
wrist.
links.
Back
Yeah,
in the day when
seriously.
you didn't have to walk around with a full atmospheric suit,
Yeah, seriously.
and the neo-proletariat haven't uploaded themselves into the internet.
Back in the day when, like, we still thought global warming was a hoax.
it's not.
No, I know. Like back in the day, like back in the day, right? But okay.
No, that was see, internet sarcasm
Okay.
doesn't work.
Even if you say it like with a certain inflection, it still gets lost along the translation.
I know. I literally hate this so much.
Like if we said the exact same thing to each other in person, you would have just got the context immediately.
Exactly.
Of course.
There's apparently closed captioning. Can I close caption our meeting? That would be terrible.
You try it out.
Ah,
And
okay,
she's
cool. I don't
back.
have to do it no more.
Oh, she's
Thank
back,
God.
she's back, she's back, she's back.
Scared the crap out of me.
We're adrift in the middle of space. Just
We're
a crew
lost
of
at sea.
monkeys. A crew of monkeys.
Hi guys, I'm really sorry. This may happen a lot this semester. I'm not sure why, but it is what it is. So we're just going to have to go. Well, I'm going to try to talk really fast now to make up for lost time. Okay, so I'm not even.
Please,
Did
no.
she,
Oh no!
Oh no! Okay, this is gonna be a really niche joke, but have any of you seen like the really terrible SpongeBob special where like Patchy invites all of the like B-list celebrities and they do various musical acts in the Nickelodeon studio?
I don't think I've
Jesus
seen that
fucking
one.
Christ. Yeah, I know that this is like back in like, my God, this is way back at least 2009.
You mean like the party he throws? Like with the mermaid in the back?
Yeah,
I'm not sure, but Pink came and like they sung a song about scurvy. That's what I imagine us doing right now. Like all
Okay, I don't
28 of
remember
us.
that though. No.
All 28 of us is thinking about how we have scurvy and we're vitamin C deficient. No, my God, I was a weird fucking kid. Fuck.
I'm having like a feeling of like despair, but it's like something
Despair?
different from despair.
Just look at David's amazing mutton chops, and you'll
Foreboding.
feel
Hey.
a lot less despaired.
I'm thinking of shaving this real soon. I
Really?
don't know. Yeah, I can't like. I don't know. I guess the novelty wore off.
You look like you play way too much Red Dead.
I actually have not touched the Red Dead game yet, much to my like immense chagrin. Every day I wake up with tears in my eyes because I haven't bought like this $80 game that my computer can't even run without like detonating.
Oh shit.
Like, I heard Red Dead Redemption 2 is one of like the best like games in terms of graphics, and so I don't want to experience that outside of like the full intended effect. So I'm not gonna like let my potato computer try to like work above its pay grade and risk me blowing my legs off.
Dude, you really do look like a Red Dead character.
It looks like you have
Okay.
six shooters, like
All you
all
do is
stashed
make
in
it
you.
beautiful.
This is true. Whenever things don't go my way during Zoom meetings, I pull out my nines, you know. I'm sorry, sixes
Pull
or
out your Lamat.
45s.
Get
I should
to
say.
work.
You're 6'6". You don't even
Right.
bother reloading. You just pull out another gun.
Seriously, it's like that scene in Django Unchained, but instead of two guns, I pull out like an entire burlap sack of guns. All right.
Are you Filthy Kong, or are you just shouting at a YouTube channel?
My network bandwidth is low. Oh no. Am I about to get sniped?
The fucking CIA is already
I
like
got dropped about
infiltrated
20
this
minutes
meeting.
ago and came back.
I didn't even consider teaching this. No.
Okay, quickly. Does anyone here remember like the orientation of the graph? Because frankly I already forgot. I just have this circle on my like.
I think it was going clockwise.
Long
I'm
ways is up and
real with
down.
you.
4 up,
I
3
put
to 5,
counterclockwise, but
counterclockwise.
it should. I think it should go clockwise more than likely.
I'm just gonna regraph it.
This
Mine graphs too fast.
I think it should go clockwise, like the
you
fucking
trace
graph,
on the
like
graph?
change orientation depending how we feel about it.
If you trace on the graph and you increase your t by 1 every time, it'll show you where it's going.
Oh, really?
Yeah. So just trace and then 1, 2, 3, and it'll show you what direction it's headed.
That's good, because mine like instagraphs everything. It's impossible to see it.
Okay. It is indeed going counterclockwise.
Yes, it was going counterclockwise.
All right. So, how are we going to solve for this t, though?
And then since it's an ellipse, just use the ellipse equation and you have the intercepts. So x squared over a squared plus y squared over b squared equals 1.
Yeah, that sounds like a reasonable deduction. Does anyone here have like previous versions of Rasky's course reader that we can use to like solve this problem in the here and now?
I mean, I still have the Calc 2 one, but
Yeah, I got the Calc 2 one.
And allegedly we did this in Calc 2, right? Like this is the right stuff?
Supposedly.
Supposedly, cool, because I forgot Calc 2 while taking Calc 2. So like...
Yeah, me too.
Apparently we took conics in Calc 2. I don't even remember a smidgen of that.
Yeah, I don't know. Hold on, who was like the host?
Actually, he was claiming that conics was in pre-calc, like even earlier.
That's Alzheimer's time.
Statistically, it had to have happened, but like I'm pretty sure we've all like prematurely aged to the point where like we don't remember anything like past last week. Oh.
Thank God.
Oh, cool. I was really afraid of being the teacher.
Cool.
Okay, I'm going to skip now all this stuff, so you're just going to have to study all that on your own. Let's get to it. I want you to go read about it.
Okay.
I'm really sorry, but I'm going to like lecture overtime, and it is what it is. Okay, and this could happen more in the future, but what can we do? So now, how do you parameterize? So how do you go backwards? Like, in other words, let's say somebody gave you a rectangular equation, and let me finish this one. So basically, you just plug it in. So you go, oh, a cosine is x over 3, square it. Sine squared of theta is y over 4, square it, equals 1. You're pretty much done. Although you may want to clean it up and make it look a little bit prettier so it looks kind of nice. And I hope you get that that is, in fact, an ellipse equation. Okay, I don't have time for letter G. Now let's talk about parameterizing. It's really important that you know how to parameterize curves. The word parameterize is going to come up, especially in November. And if you don't know how to do it, I'm going to go, hey, remember Wednesday, September 9th? The idea is you're given a single rectangular equation. You give me a vector valued curve. And yes, it's on the homework. So you start by doing R of t, or if you prefer V of t, but it's got to be a nice notation. And I prefer brackets. Now for functions of x, I'm going to teach you the 3 possibilities. Okay, so this is the idiot-proof Rasky way. If you have a function of x, which letter h is, and y equals x cubed plus 1, that's a function of x. Beautiful. It's super easy. All you do is you let x be t. There's one of the parametric equations. And then, since y is x cubed plus 1, y is t cubed plus 1. Boom, I'm done. Now, if you want to prove it to yourself, you could graph this in parametric mode on your calculator, and I claim it's going to be the exact same graph as y equals x cubed plus 1. Have fun. Now, what about functions of y? This right here is a function of y. Well, how do I know? Well, because x equals y squared minus 4, that's one of those horizontal parabolas. So if you have a function of y and somebody wants the parameterization or the vector valued function, you're like, and by the way, we did this in Calc 2, we just didn't do vector valued functions, we just gave the parametric equations. You let y be equal to t. And since x is y squared minus 4, x is t squared minus 4, and boom, I'm done. Now, folks, this is really cool. Why? You should all be like paying attention here. On your graphing calculator, you already know that if you have a function of y, like y equals x cubed plus 1, you use func mode and you can graph anything as long as it's a function of x. But you don't have the capability in func mode to graph functions of y. Now you do. You just get into parametric mode, you let y be equal to t, and then the x will be whatever is based on, since it's a function of y, and you're done. Now this one is neither a function of x or y. It's a circle, so it doesn't pass the, the vertical line test. So what do? Well, you get on your knees and pray it's going to work out. Usually you can use like some sort of Pythagorean identity from trig or something like that, which I'm actually going to do. So I'm going to divide both sides by 16. Well, how come? Because I'd like to use cosine squared theta plus y squared, or sine squared theta is equal to 1. And that has that sort of flavor to it when I have a 1 on that side. So then what I'm going to do is I'm going to rewrite this as a sum of squares, and then I'm going to claim that that guy is my cos theta, or t if you like, I don't care what your parameter is. You can use theta for a parameter. And your y over 4 is your sine theta. And then, so then what? So then if you write this down, x over 4 is cos, and you solve it for x, x is 4 cos theta, and here you say y over 4 is sine theta, and then solve it for y, you get y is 4 sine theta, and then your vector valued function will have theta be the parameter instead. I don't care if it's t or theta, whatever the hell it is. Later on we're going to do s, which is arc length parameter, but I don't want to scare you yet. Okay, so there we have it. There we have a vector valued function, and that's going to be a circle. Okay, now this is not a trick question. This is to see if you've actually been awake all last week. If you had a vector valued function that had 2 plus t, 3 minus 4t, and negative 1 minus t, it's a 3D curve. I claim everybody in the room should know what the graph of that looks like without even having to graph anything in 3D. What would it look like?
A line.
Yeah, how did you know that's a straight line? Very good.
Because it's because the equation for a line that we learned previously were 3 parametric equations.
T plus t. Yeah, exactly. Y equals 3 minus 4t, and z equals negative 1 minus t. Doesn't that have the flavor of the parametric equations for a line? Yeah, so it's a straight line, which is put into vector valued function format. Okay, now let's talk about domains. Now, I give you a procedure here. Let's go over it. This is an idiot-proof procedure to find domains of vector valued functions. First, you assume it can eat anything. What does that mean? All values of t. So don't just put real numbers, because I'm going to not give you credit. Like what I mean is t can be anything from negative infinity to positive infinity. You start off pretending your function has all reals as the domain. And then you start worrying as you look at it if any of the components are trouble components. So what is the possibility of a trouble? If one of your components has a denominator where there's a variable in it, you never want denominators equal to 0. That's bad. So then you have to figure out what values of t, your parameter, would make that denominator equal to 0, and you throw those out. Those aren't going to be part of your overall domain. Another worry spot is even radicals, like square root of t, for example. You don't want to take square roots of negatives. Square root of 0 is fine, and square root of positive is fine. We're not going to get into the imaginary world in this class. So you want to eliminate any values of t that would make your radicand negative. Sorry, what I was doing there. Trying to get rid of this. You know, I'm not a fan of teaching face-to-face. I am a fan of teaching face-to-face. This online is for the birds. It's for the birds. Okay. Are there any logarithms in there? Because like if you had ln of t, say, as one of the components in your vector valued function, that you'd be screwed if you try to take ln of, say, 0, because that's not defined. Or ln of negative 4. That's not cool either. So you want to make sure if you have any logarithms in there that only positive arguments occur. Okay, and then finally arcsine and arccos, your argument has to be in the range of negative 1 to 1. Then this is the hard part. You have to intersect all 3 sets to come up with common ground for t. And this is the part where students choke. And then I always put really cool problems on there and they can't figure it out because they don't know how to intersect sets. They know how to do all the components individually because that's like pre-calc knowledge. But then when it comes to intersecting the set. So I'm going to do a couple of these problems. I'm going to try to do it as nicely and easily and gently as I can. So I'm going to give you the Rasky experience. Here we go. Step 1. First assume that this vector valued function can eat all values of time t. But he can't. It turns out there's restrictions on his diet. Well, what do you mean? He's got a logarithm right there, ln of t. You got a restriction because t had better be strictly greater than 0 for that particular component, okay? The middle component has no restrictions on its domain because t can be t. Now, the last component, you got restrictions because you need or want the radicand to be greater than or equal to 0. And if you solve this for t, you get that 1 greater than or equal to t, which means the same as t less than or equal to 1. Now you have to intersect all your sets. What does that mean? I'm going to use colors. I'm not trying to insult your intelligence, but if you use sort of this color-coded Rasky way, you won't screw up. First off, if I graph and shade in, let's have this be the t-axis. Here's the 0. If I shade in all the values that are strictly greater than 0, I'm going to put an open bubble around the 0, and all the values to the right of t are shaded in. So I'm going to shade that in. Beautiful. Now what? The middle component has no restrictions. So his t-axis, I could shade in everything. Okay, I'll shade in and even shade in the arrows because it goes on forever in both directions. Okay, there's no restrictions. Now the last guy, he's got a little bit of, by the way, you want to line up your zeros here when you put your 3 axes down. Here's the zeros. This guy, t is less than or equal to 1. So I'm going to put a little bubble there, but I'll color it in because he can eat the 1, and then I'll shade in all the values to the left, because less than, and it goes on forever and ever to the left, all the way to negative infinity. Now, here's the hard part. In your mind, please imagine all 3 of these number lines collapsing into a single number line. What values of time t would have all 3 colors on them at the same time? That's your answer. So what values of t would be blue, red, and green at the same time? So you're going to intersect the sets. Does anybody see it?
0 to 1.
Yeah, 0 to 1. And then are you going to put a parentheses or bracket on either end, or what are you going to put there? And yes, it matters. Emily has it. Thank you, Emily. She put it in the chat box. Perfect. Thank you so much. You're going to have parentheses because it's not including the 0. And you'll have a bracket on the 1 because you are including the 1. And that's the answer for part A. The t can be any element in 0 to 1. And it's not a very big domain. It looks like you can't eat very many values of t, right? No ice cream for you. Okay, and so that's how you would do that one. I'm going to do one more. Let's do letter B. Letter B is a little tricky, but that's how I roll. So what about absolute value? Does that have any restrictions to his domain? So this first component in letter B, absolute value t plus 2. Any restrictions?
No.
No. If you read the rules on the previous page, the range of absolute value is restricted. The domain is okay. So no restrictions. He can eat anything. Okay, fine. You would shade in the entire t-axis. Okay, fine. How about the second component? Well, we got a problem because we don't want the denominator to be equal to 0. That would be bad. Well, here's what I'm going to do. I'm going to actually set the denominator equal to 0 and then solve this quadratic equation. And the solutions I'm actually going to throw out. He can't eat those numbers. And this particular quadratic equation, I mean, you could use the quadratic formula, but that's overkill. I'm going to actually take away points from you if you use the quadratic formula when you don't have to and waste valuable time. Okay? It's easier to factor and apply the ZPP, the zero product principle. What's the zero product principle? The ZPP says if something times something equals 0, then you set those individual factors equal to 0 and solve those. And I get 2 answers. And this is not the answer. This is what you don't want. So if you were looking at the t-axis here and you were shading in the values that he could eat, you would put an open bubble around the 3 and the 5. You would shade all the values in between 3 and 5. And anything greater than 5 and less than 3 would be okay values in the domain. Then what? The last component is a square root function. Uh-oh. Well, square roots do have restrictions because we don't want to get into the world of imaginaries. So we're going to go, okay, we need that radicand to be greater than or equal to 0. Then what? If you solve it for t by subtracting 2 from both sides of the inequality, t is greater than or equal to 2. So if I sketch this number line, I'll try to use a different color here. Remember, the first one was just all real numbers, so I'm not even going to bother. So here at the -2, and then I'm going to have a bubble there, but I'll color it in because -2 is actually an okay value. And then I'll shade in all the numbers greater than. If you can imagine in your mind, if my PDF annotate would cooperate, these two number lines collapsed and you want to intersect these two sets, what value of t would be in both sets? Which values of t would be both red and blue at the same time?
Be greater than or equal to -2, but yet to exclude the 3 and the 5.
So you're going to go like this. This interval union the middle interval between 3 and 5 union 5 infinity. And so t can be an element of any of those three intervals, and those intervals represent the entire domain of that vector valued function. So that's basically how you roll when you're finding domains of vector valued functions, is you figure out the individual components and then you try to intersect the sets. That's it. There's no calculus involved, but you do have to know about domains. So you do have to have some strong pre-calc skills. Okay, let's do limits, because I can. How do you take a limit of a vector valued function? Very carefully. And it's really easy. You're going to love this, because all you do is, once you're given either a 2D or a 3D vector valued function, it's going to equal a vector where the components are simply the individual limits of each of those components of your vector. That's it. It's that simple. Oh my goodness. Really? Yeah, really. Now the picture of it, if you're going to look in 2D here, I just have a picture. If you have your curve here, and here's your r of t, remember it's a vector, and suppose you do have some limit L as being your answer. The difference between these should get squeezed down to 0 the closer and closer your r of t gets to your limit L, as time goes to some value that you're going to. So your limit basically ends up being the difference between two vectors, and you want it to approach 0 if a limit exists. Okay? I'm not going to get too much into that. If you're still confused, don't worry about it. Let's do some Calc 1 and Calc 2 review. I didn't have this in my last course reader. If you got a hold of last semester's course reader, sorry for you, because I've made some changes over the summer. So I put this in here for a reason, because of the fact that I noticed a lot of people, even though they supposedly had limits in Calc 1 and Calc 2, by the time they get to my Calc 3, they're still not good at limits, which kind of sucks. So I'm going to give it to you again. Let's do some limit facts that you should not lose sight of. What is 0 divided by a number where c is a non-zero real number, like 2? What's 0 divided by 2? Quick.
0.
Very good. Number 2, what's infinity divided by some non-real number, non-zero real number, like 2? Infinity divided by 2 is still?
Infinity.
Infinity. Beautiful. How about logarithms? If you look at the graph of ln x, these two logarithm facts are kind of easy to figure out. When x gets very, very large, so you're taking a limit of ln x as x goes to infinity, what's the log function approach?
Infinity.
Infinity. On the other hand, if you're approaching 0 from the right, the log function is approaching what? I'm giving you a hint here.
Negative infinity.
Negative infinity. So ln of 0 is not really defined because it's a limit. It approaches negative infinity. Okay, we're done talking about ln of x. How about 1 divided by a very large number? 1 divided by infinity. What does that really approach?
0.
0, very good. So anytime you see 1 over infinity, think, that's 0. Now let's look at exponentials. If you look at y equals e to the x, like so, e to the negative infinity, so when you approach negative infinity, what is your e to the x approaching?
0.
0. How about e to the positive infinity?
Infinity.
Yeah, it's just growing large. And the same whether your base is e or an a. So as long as your a is some number greater than 1. This will also be 0 as long as a is greater than 1. This will also be infinity. Okay, we're done with exponentials. How about 1 divided by 0?
Infinity.
Yes. And what about if it were negative 1 over 0?
Negative infinity?
Yep, you got it. Okay, keep going. And this one's a tricky one. What about cos infinity? I claim it gives you the same answer as sine infinity. The answer is DNE. Does not exist because it just oscillates between 1 and negative 1. So you never settle down. On the other hand, if you have a cosine or a sine, contained in the numerator and you have something in the denominator that grows large, so we're talking about growth rates, then even though this numerator may be oscillating between plus or minus 1, if your denominator is growing large and larger and larger, this will approach what?
0.
0. Good. And similarly, sine of x over x approaches 0. Now let's do some arctan facts, and then we'll actually do some real life problems. If you remember from Calc 2, the graph of arctan has kind of a cool look to it. It's got two horizontal asymptotes. So it does have nice values for limits at positive and negative infinity. So arctan of positive infinity is?
Pi over 2.
Yeah, and arctan negative infinity?
Negative pi over 2.
Yeah. Don't lose sight of those facts because I like to test those a lot more than Briggs. Well then, but if your homework's based on Briggs, then how do you do it? Let me tell you a secret, guys. You're going to hate me, but I spent my whole summer on my math lab. I created a lot of custom-made questions that I stuck in your homework and your quizzes, and that's what my whole life was over the summer, is making my math lab quizzes.
God bless you.
Thank you. You're welcome. And the good news for you is sometimes I would make a quiz, and then, you know, of course, I had to do it, unlike some of the other ones I did last semester. And when I'd be doing it, I'd be going, this is too long and too hard. Screw this. And so I'd redo it and make it shorter because I felt your pain. You're welcome. So let's do a limit problem, and then we'll be done, and we'll pick this up next time. Okay, so let's just do one of these pups, all right? First up.
Professor, did you cover the other limit facts, or you skipped those?
Oh, did I?
The
12
through 17?
Oh, yeah, okay, sorry. 0 over infinity, I thought about these. This is 0. Infinity over 0. Does anybody know this one? This is hard.
I don't know.
It's infinity.
Super infinity? Okay, never mind.
It's okay. How about 0 to the infinity?
At 1? I don't know.
0?
Yeah. And 0 to the negative infinity?
Still 0.
Yeah.
Negative 0.
Okay. Now remember, 0 to the 0 is indeterminate, and 1 to the infinity is indeterminate. Do you guys remember this?
Yeah, and you have to take a real special case.
0 is indeterminate, so you have to be careful. But infinity plus infinity, infinity. Negative infinity minus infinity, negative infinity. However, you have to be careful, because infinity minus infinity is indeterminate. Okay, let's move on. Okay. All right. So let's keep going. We got more crap to do. Okay. Find the limits if they exist for the following. Okay, do you guys remember L'Hopital's rule?
Like the derivatives of the top and bottom, I think.
Okay.
Yeah. 0 over 0.
Yeah, if you get an indeterminate like infinity over infinity or plus or minus these or 0 over 0, then use L'Hopital's. Okay, so first up, you always try direct substitution. So when you take the limit as t approaches 1 of this guy, this creature, I get, ooh, crap, I get indeterminate. Now what?
L'Hopital's.
L'Hopital's, LH for short. So you're still going to take a limit as t goes to 1, but you're going to take the derivative of the numerator and divide that by the derivative of the denominator, and now use direct substitution. And what do you get? A nice number. Save that for later. Now take the limit as t approaches 1 to the middle component. So again, just substitute. So what is ln of 1?
0.
0. Save that for later, because we're going to put it all together. How about cos of 3 pi t, where t is 1? What's cos of 3 pi equal to? Anybody know this?
It's going to be negative
That's
1.
right.
Yeah, that's negative 1.
Okay, now put it all together in a nice vector valued, or a constant vector. So the vector answer is 3, 0, negative 1 in that order. So the limit exists, and the limit is that beautiful constant vector, and we're done. Okay? I know. I'm going to stop the lecture there. Thanks for putting up with my wonky internet today. Sorry about that. Thanks for staying late. See you later. I'm going to post the recording this afternoon, okay?
Oh no! I think we recorded the parts where like you went off and we basically declared a free state. I mean...
All right. Well, that'll be interesting. Your sovereign state. Okay. Any other last minute things? Because I'm going to stop share. I got to go to a Calculus 2 class.
Professor Rasky, when you were doing the domain problems for the vector valued functions,
sure.
Would you prefer interval notation? Like,
yes.
For example,
I do.
One problem where you,
I do, but my math lab may ask you for something else. Sometimes they ask for interval notation, so be careful what they ask for. And sometimes they'll ask you for, oh, just t greater than whatever, and give some sort of inequality.
Okay, thank you.
So it depends on my math lab and how they're going to roll there. All right, Isaiah, I see you in Calc 2. David, do you want to see me in Calc 2 also? Okay, I'm done. Bye.
Thank you.